Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we are going to look at the quantitative side of acid and base chemistry, which is the calculations of hydronium hydroxide, pH, and pOH. Where I would like to start with, though, is where does the idea of neutral even start with? And of course, the idea of neutral is you have an equal amount of acid and base. Now, the perfect example of an equal amount of acid and base is when two water molecules react and one of them donates a hydrogen to the other to create an acid and a base. Is perfection in terms of neutral. One acid would cancel out one base to make pure water, which is essentially pure neutral. Now, if you were to analyze two water molecules in a billion, this is what would happen. 2 in a billion would actually have this reaction happen. If you were to work that down into a concentration in terms of moles per liter, it would be 1.0 times 10 to the negative 7 moles per liter of hydronium and 1.0 times 10 to the negative 7 moles per liter of hydroxide. Because that is an equal amount of acid and base, it means that they are completely neutral. Now, when you add an acid or base to a water, it's going to shift this system to one side or the other. So what I want you to understand is when you have something that is acidic, it doesn't mean that there is no base. What it means is there's less base than there is acid. Try to think of it almost as being a sports team. Just because one team is winning, it doesn't mean the other team doesn't exist. It's just there's more of one higher score than the other. And so my biggest example is this. I'm going to call this a pH of 7, which is neutral. I'm going to call this a pH of 1. I'm going to call this a pH of 14. When you have something that is very, very acidic, it tips the scale of hydronium to hydroxide in the favor of hydronium. You have lots of it. Now, as you become less acidic, you have less of it. So when I look at this side of the scale closer to 1, it doesn't mean I don't have any hydronium. I actually have a little bit of hydroxide. And as I get closer to 7, I get a little bit more hydroxide and a little bit more hydroxide. At pH 7, you essentially have the same amount of hydroxide as you do hydronium. As we approach a higher basic level, we have more hydroxide than we have hydronium, and the hydronium tails off. Now this is in proportion, so if I increase the concentration of a hydroxide 10 times, that means I decrease the hydroxide concentration 10 times. As one goes up, the other one goes down by the same amount. So again, if I double this, I half this. If I quadruple this, I quarter this. If this is 10 times bigger, this is 1/10. They are in proportion to one another. As one goes up, the other one goes down in proportion to it. Okay, so again, what is acid is hydronium, and what is base is hydroxide. Now, to communicate how strong something is acidic or basic in terms of moles per liter to the average person in a community would make no sense. Just think about it. If you told your mom that orange juice is really acidic and that it had a concentration of 2.0 times 10 to the negative 3 moles per liter of hydronium, she would have no clue what you're talking about. But if you said to your mom, this orange juice is really acidic, it has a pH of 3, she would have some concept of what's going on. And realistically, the calculation for pH is just to make a concentration, which is very bizarre in terms of scientific notation in moles per liter for your average person, into a value that really anybody can understand. If I fed my 4-year-old an orange and it was really acidic, and he said, "Ooh, it's really sour, it's really acidic," and I had to explain to him like pH, and I said neutral is like drinking water, and this is like pH 3, that's really acidic, he would grasp the concept of that, whereas if I told him it in moles per liter, he would not understand what's going on. So for instance, I'm just going to use this as an example. So if you have a glass of pure water, the concentration of hydronium is 1 times 10 to the negative 7. If I want to calculate the pH of that, I would take the negative log, that's logarithm, base 10 logarithm, of the hydronium ion concentration. So what that would be is the negative log of 1.0 times 10 to the negative 7. Now, if you know anything about logarithms, more specific base 10 logarithms, if you have 1 times 10 to any power, negative power, it is that value. So the negative log of 1 times 10 to the negative 7 is literally 7. 7 is neutral. This is where we get the idea of 7 as being the value for neutral. It has nothing to do with somebody liking the number 7. It is literally the negative log of the concentration of hydronium, and that's where it comes from. Now, we're also going to come across this POH, which has to do with the amount of base. Now, if I take the negative log of the OH concentration, that's the POH. Well, the negative log of the exact same number is the exact same number. It's times 10 to the negative 7 becomes 7. So something that is purely neutral has a pH of 7, and it also has a POH of 7. And always, pH plus POH is equal to 14, which our pH scale is based on. So in this case, this is 100% true. 7 plus 7 is equal to 14. That is the pH plus the POH. It is equal to 14, which is neutral. This is where the concept of neutral is. Now, if this goes up by a value of 1, that means this has to go down by a value of 1. And that's what we're really working on today, is how does this all come together? And this is kind of our first look at the actual calculations involved in pH and POH. In the next section of our lesson, we're going to look at taking acid or base information or both and turning them into something different. Now, the equations in this chart need to be memorized. You will use them in Chemistry 20, Chemistry 30, and any chemistry that comes beyond this for you. So I just want to talk about the 3 different columns here. The acid column is strictly dealing with base information quantitatively, whether it's hydronium or pH or hydronium and pH. The base side of this is 100% base information. It is POH, which is the power of hydroxide, or the hydroxide ion concentration, or vice versa. So if I'm given base information and they ask me for the opposite, so if they give me POH and they want OH, or they give me OH and they want POH, I can convert one to the other with using these equations in one step. But if I was told the pH, but I wanted to figure out the hydroxide ion concentration, I'm gonna have to do a switch equation in some kind of pattern to get over here, and this would be a 2-step process. So if you look at all the switch equations, they have things that involve both acid and base. pH is acid, POH is base. Hydronium is acid, hydroxide is base. Ka is acid, Kb is base. Now, this equation here, we're going to do a bit of a conversion to it. At our level, we're really looking at Kw is equal to the hydronium times the hydroxide, which you will see here, which is exactly the same as this. This is more of a Chemistry 30 idea. So really, we have 6 equations to learn, and you'll notice they have a lot of similarities. The one I want to point out immediately is in our previous question, the POH plus the pH had to be equal to 14, and sure enough, that is a switch equation. Acid information, base information, it has them both. We'll start with some easier questions that are dealing strictly with one-step problems. So with these acid calculations we're first going to look at, they're going to be dealing with only acid equations. Let's start. So the first one is turning a hydronium ion concentration into a pH. It says, calculate the pH of a solution with a hydronium ion concentration of this value. So pH is equal to the negative log of the hydronium ion concentration. I really want to point out this negative is extremely important. If you do not include that, it's going to change your answer drastically. So look, we'll put in our numbers. The negative log of 3.05 times 10 to the negative 3 is equal to, and if I plug that into my calculator, I get 2.52 with rounding as my value. Now, this looks like the right number of significant digits because this is 3 significant digits. But in reality, the number of significant digits actually represents the number of decimal places in a pH value. Now, the number of decimal places right now is 2. I actually need a third. So if I go back to my calculation, I will find that this is actually 2.5157. Now, it's the last digit behind my last significant digit that affects rounding, and this will round this up. So my actual answer in the end is pH is equal to 2.516. It seems bizarre. This number looks like it has 4 significant digits, but it doesn't. These 3 decimal places represent the number of significant digits, and this value has 3 significant digits, so this actually matches. The next question we're going to do the exact opposite. Instead of starting with hydronium and turning to pH, we're going to start with pH and we're going to turn it into hydronium. Now, in order to do that, we're going to do the inverse equation, which is this. The concentration of hydronium is equal to 10 to the negative pH. So if I was to plug this into my calculator, it would be 10 to the negative 3.42. And if I put that in my calculator, the answer comes out to 3.80189 times 10 to the negative 4. And because this is a concentration, it's in moles per liter. Now, if I was to round this properly, when I look at this value up here of pH, it looks like 3 significant digits, but only the decimal places are significant. So I only need 2 significant digits. This should come out to 3.8 times 10 to the negative 4 moles per liter, and that would be equal to the concentration of hydronium. So the next thing we're going to look at is dealing with really a lot of common mistakes made by students around increasing the value of hydronium or hydroxide by a power of 2 or 10, etc. And what you need to realize is that because a logarithm is base 10, when you move one value one way or the other, you've increased it by a factor of 10. Now, normally people think that if you double the amount of base or double the amount of acid, it will move the pH value 1, when it actually doesn't. It barely actually moves it. So let's look at these 3 questions here. It talks about the pH change factors, and it starts by saying that a solution has a pH of 7.50. And then it says, what will be the pH of this solution if the hydronium ion concentration is increased by a factor of 10? Now, again, a lot of students would think, well, it would change the pH by a value of 10, so to whatever, -2 or so. But it actually just changes the value of the pH by 1. So, for instance, if I'm starting with 7.500 and I change the amount of hydronium by a factor of 10 and make it more acidic, that changes the pH by one value to 6.500. This would be 10 times more concentrated acid. For B, if I increase the value by 1,000, I would have to essentially move that over 3 times. So I would go over to 6.500. This would be true if this was 10 times more concentrated, but it would be 5.500 if it was 100 times more concentrated. And if I moved it to 4.500, that's 3 times over, which would be 1,000 times more concentrated, which is crazy. So again, if you notice, I've got 3 zeros in this number, and I've moved this over 1, 2, 3 times to get the actual pH. The hardest question here isn't a 10 or 1,000. It's something like doubled or tripled or quadrupled. So if a solution had a pH of 7.5 and I wanted to know what the pH would be when I double the concentration of hydronium, it actually requires a couple of steps. I'd first have to figure out the amount of hydronium by taking it to 10 to the power of the negative pH. And so in this, it would be 10 to the negative 7.500. And this would give me a value of 3.1622, so on and so on, times 10 to the negative 8 moles per liter. Now, if I doubled the amount of this, that means I'd have to multiply it by 2. And when I multiply by 2, I get 6.3, 245, etc., times 10 to the negative 8 moles per liter. So that's double the concentration of hydronium. Now, if I was to turn that back into a pH, which is what it's asking, pH is equal to the negative log of this value, so 6.3245 times 10 to the negative 8 would be equal to 7.1989. And if this has 3 decimal places, my answer needs 3 decimal places. So I underline the first 3. I circle the number behind it. This rounds this up to a 9. This would be a pH equal to 7.199. So in the next section of our acid calculations, we're going to look at some more in detail questions with more steps. So in the next one, we're going to look at taking a mass of an acid and turning it into a pH. So the question says, if 3.5 grams of HCl is dissolved in 100 milliliters of water, what is the hydronium ion concentration and what is the pH? Now, when we look at something like HCl, which is a strong acid, it would react with water 100% to turn into hydronium and chloride ion. And this is a 1 to 1 to 1 to 1 ratio. So what it essentially is saying is the concentration of HCl is actually equal to the concentration of hydronium, because stoichiometrically they are 1 to 1. So if I know the concentration of HCl, then I know the concentration of hydronium, which is our first question. And then I can turn that into a pH. Well, in our previous lessons, we learned that concentration is equal to mass over molar mass volume, where we're essentially subbing in moles as mass over molar mass. Now, the mass of HCl is 3.5 grams, and the molar mass of HCl is equal to 36.46 grams per mole. And converting the volume into liters, it would be 0.1000 liters, because this has 4 significant digits. Double bracket the bottom, and I get an answer of 0.95995 at 6 moles per liter. Now, this is our first question. I'm going to give it its formal answer in correct significant digits here, even though in the second part I'm going to carry all the digits over. So the concentration of hydronium to 2 significant digits, this is 2, this is 4. So 2, the 9 rounds this up, is 0.96 moles per liter. So that's the question, the answer to our first question. Our second question is, what is the pH? Well, pH is equal to the negative log of hydronium, and we have that value. So it's the negative log of 0.96 moles per liter. Now I'm going to use all the digits in my calculator. I'm going to carry everything forward. And if I do that, I get a value of 0.01778. So the pH, based on my number of significant digits, which is only 2, which is 2 decimal places, the 7 would round this up, would be 0.02. The next question we're going to look at, we're going to convert a pH to a pOH. And the easiest way to do this is using this equation. pH plus pOH is equal to 14. Now, to rearrange that, I would move pH over by subtracting pH. And so my equation would become pOH is equal to 14 minus pH. So this would be 14 minus 5.6. And if you put that into your calculator or just use mental math, it would be 8.4. 1 decimal place, we are correct. Now the next one is essentially the exact same equation, but not base 10. It's not an actual integer value where it's the power of. It's essentially this. Hydronium ion concentration times hydroxide ion concentration is equal to 1.0 times 10 to the negative 14. Now you'll notice the common connection of 14 here, and that this is the power of hydroxide. This is the power of hydronium. It looks very, very similar because mathematically it is very, very similar. Now, what we're going to do is we're going to solve for hydronium. So we're going to divide the hydroxide across to the other side, like so. And so my hydronium ion concentration would then be 1.0 times 10 to the negative 14 all over the concentration of hydroxide, which is 1.22 times 10 to the negative 3. Now, if you plug that in your calculator, you're going to end up getting a value of 8.1967 times 10 to the negative 12. Now this digit has 3 significant digits, and this one has 2, so it's going to be 2. This is going to round up, and the concentration of hydronium is equal to 8.2 times 10 to the negative 12 moles per liter. Our last one here is going to be a 2-step problem, and I'll tell you why I know it's 2-step. What we're going to start with is a pH, which is acid information. Hydronium and pH are based on acid, hydroxide and pOH are based on base. When I want to go from one to the other, I either have to use just a switch equation, like one of the two above, which is really simple, or I'm going to have to use a switch and then one of the other equations, whether it's acid or base. These questions always have 2 possible answers, and I am only going to solve for these ones in one way, but there is more than one way to solve them. So this one says, calculate the hydroxide ion concentration of a solution with pH. Well, pH is acid and hydroxide is base. That means I'm for sure going to have to use a switch equation, but probably another one. So the way I see it, the easiest to solve is to start with this one. pH plus POH is equal to 14. And POH is base. I can turn a POH into a hydroxide ion concentration really easily. So I'm going to make this POH is equal to 14 minus pH to get the POH first. So 14 minus 6.66 is equal to 7.34. This is the POH. So this is my first step. I've converted the acid information to base information. Now I need to do a conversion within base. So in my second step, I'm going to get the hydroxide ion concentration by taking the POH and going 10 to the negative POH. So this is 10 to the negative 7.34. And so we get an answer of 4.5708 times 10 to the negative 8 moles per liter. But if I'm doing significant digits, I need 2 significant digits, 2 decimal places in the pH. And so my hydroxide ion concentration is really equal to 4.6, because the 7 rounds it up, times 10 to the negative 8 moles per liter. Next, we're going to look at base calculations, and we're going to look at them starting very simple, so 1 step, and then we'll move on to 2 step. So we got 2 1-step calculations here. Very simple and straightforward. So the first one says, calculate the POH of a solution with a hydroxide ion concentration of 8.1 times 10 to the negative 9 moles per liter. Now POH is equal to the negative log of the hydroxide ion concentration. So in this question, it's 8.1 times 10 to the negative 9. We're going to plug that in. So this is going to equal the negative log of 8.1 times 10 to the negative 9 moles per liter. And what we would get is 8.09. Now, this number has 2 significant digits, so I need 2 decimal places in my POH. So POH is equal to 8.09. In our next question, we're going to go the opposite direction. I'm given the hydroxide ion concentration, I'm given the POH and I'm turning it into a hydroxide ion concentration. So the hydroxide ion concentration is always equal to 10 to the negative POH. So in this question, they give us our POH, so it's 10 to the negative 9.90. So we go to the power of 10, negative 9.9, and we get 1.2589 times 10 to the negative 10 moles per liter. Now, our question here has 2 decimal places as a POH, so I need 2 significant digits. The 5 would round up, and our final answer would be the hydroxide ion concentration is equal to 1.3 times 10 to the negative 10 moles per liter. In our last 2 questions, we're going to look at doing a couple multi-step processes. So with the first one, it says, if 6.5 grams of sodium hydroxide is dissolved in 100 milliliters of water, what is the hydroxide ion concentration, the POH, and the pH? So the first thing I would do is actually write out a dissociation equation. So sodium hydroxide would dissociate in water to produce sodium ions plus hydroxide ions. Now they haven't given us the mass of hydroxide, but stoichiometrically, for every 1 mole of this, there is 1 mole of this and 1 mole of this. So if I actually know the concentration of this, sodium hydroxide, it is equal to the concentration of hydroxide. So we have a few things. First of all, the mass of sodium hydroxide is 6.5 grams. Now, in order to get moles, I'd have to figure out the molar mass, and the molar mass of sodium hydroxide is 40 grams per mole. And then we have a volume of 0.100 moles per liter. All right, so if we put that into C is equal to M over MV, we would get 6.5 grams all over 40 grams per mole and 0.100 moles per liter. And putting that all in our calculator, we would get 1.625 moles per liter, which is extremely concentrated. So again, the concentration of NaOH, which is equal to hydroxide ion, with rounding would be 1.6 moles per liter. Now, in order to get the POH, I'd have to take the negative log of the hydroxide ion concentration in a second step. Now, if I do that and I go POH is equal to the negative log, and not my rounded number, I keep everything with it, so 1.625, I get an answer of negative 0.2108. Yes, people, pHs can go below 1, they could be 0, they can actually be negative, and pHs, yes, they can go past 14. This isn't actually super common, especially with household products, but it is in chemistry. So the POH, if it was rounded properly, would actually be negative 0.21. Then to get my pH, I'd have to take 14 minus the POH. So this would be 14 minus a negative 0.21. And so the pH is going to be equal to 14.21. Our last switch equation, we're going to start with a POH and we're going to work towards a hydronium ion concentration. So I know I need at least a switch equation, but probably more. So again, I'm trying to figure out acid information, which is hydronium, and I'm starting with hydroxide or base information, which is based around hydroxide or POH. So the first thing I'm going to do is I'm going to say that the pH is equal to 14 minus the POH to get it into acid information. So 14 minus 2.97 is equal to 11.03. So that was my first step. Now, the second step, I can get the concentration of hydronium by taking 10 to the negative pH, which I just figured out, which is 10 to the negative 11.03. And when you put that in your calculator, you get 9.3325 times 10 to the negative 12 moles per liter for the hydronium ion concentration. Now, with significant digits, this has 2 decimal places, so it's 2 significant digits. So 9.3 times 10 to the negative 12 moles per liter is equal to the hydronium ion concentration. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.